All right, so let's talk enzymes. So remember that enzymes are going to be catalysts that speed up chemical reactions. By lowering what we call the energy of activation, which is E sub A. And that simply just means the amount of energy that's needed to make a reaction occur. Now, my students who I've had in lecture, what is usually a telltale sign in the textbook that what you're looking at is an enzyme? What do you always look for?
ACE.
ACE. If you see ACE at the end of a word, that something is an enzyme. Not every enzyme will end with ACE, but if you see ACE, that is an enzyme. Okay? So, what we wanted to do in this experiment was we wanted to look at a specific enzyme that played a large role in a particular pathway. So, before we get to that enzyme, let's just talk generic enzymatic kinetics. Okay? So, let's just say we have some arbitrary enzyme here. So here's my enzyme. Now this enzyme has a distinct region on it here that is going to bind to a particular target molecule. What do we call the target molecule of any enzyme? The substrate. Good. And then there's a certain name for the region of the enzyme that binds to that substrate. What do we call it? The active site. So this region on my enzyme here, which I'm kind of tracing in green, is called the active site. Okay, so essentially what happens is the enzyme will bind to its specific substrate, and that active site is very flexible. So the active site can put stress on the substrate molecule and begin to change its shape until eventually the substrate is converted into products. This is how the enzyme can lower the activation energy, at which point in time the enzyme will release that product, whatever it is, and the enzyme can return to its original shape to bind to another substrate. So enzymes, I always tell my students in lecture, are very much like assembly line workers. They get a certain piece, they add that piece on, they put the thing back on the conveyor belt, and they go and they grab the next piece. Okay? Questions, concerns about general enzyme kinetics? All right, so in our experiments, there was a distinct enzyme that we wanted to focus on. And this enzyme targeted a specific substrate. So what was the enzyme that we focused on for this exercise? Lactase. Okay, there's lactase. Now the good news about some of these enzymes, and the way I know it's an enzyme, it ends in ASE, ACE. The good news about some of these enzymes is their name kind of tells you what substrate they target. So what is the substrate of lactase? Lactose. One of my students for Gold Star, what kind of molecule is lactose, but it isn't OSE? It's a sugar. Ose always means sugar. Good. Now, the overall reaction that we were looking at here is the metabolism of lactose. During this reaction, lactose is broken down or hydrolyzed into two monosaccharides. So this is a disaccharide that's broken down into two monosaccharides, and those monosaccharides are galactose and glucose. So what you all wound up doing was you wound up using glucose as a way of measuring the effect that lactase had on this reaction. Now, in case you're scratching your head still from this exercise and wondering, how could we do that? Well, let me go ahead and pitch this to you. So, we have this reaction where lactose becomes galactose and glucose. So if we measure the amount of glucose, that, in theory, tells us how much lactose has been broken up. if lactase being added to a tube produces more glucose, then that tells us that lactase is making the reaction happen faster. Does that make sense to everyone? Okay. So what this means is we can use glucose as a measurement of lactase activity. The more glucose I have, the higher the lactase activity. The less glucose I have, the lower the lactase activity. Everybody get that? Okay. So there was a fundamental question we asked for the first two experiments with this lab. And that was, this lactase that we're looking at, did it come from humans or did it come from bacteria? And we used the first two experiments in an attempt to answer this question. Okay? So, let's talk a little more about what we expect to see in human lactase versus bacterial lactase. So, the first experiment that you performed was to determine the optimal temperature of lactase. So to perform this experiment, you had a variety of different temperatures. You had 0 degrees Celsius, 25 degrees Celsius, which is room temperature, 40 degrees Celsius, 60 degrees Celsius, 80 degrees Celsius, and 100 degrees Celsius. But again, we're trying to determine if this lactase in question came from humans or bacteria. And the specific type of bacteria we're interested in is one that's commonly called a thermophilic bacteria. Now, one of my students, what does philic mean? Loving. Thermophilic bacteria love living in warmer environments. So, what we're trying to determine here, did it come from bacteria or humans? So let's talk about what we expect to see in terms of glucose levels if it came from one of these organisms over the other. Okay? So, with humans, let's first and foremost talk about this. So, remember that the optimal temperature is the temperature where the enzyme works the best. So what should I expect to see in terms of the amount of glucose produced at the optimal temperature? Will it be the highest or the lowest? Highest, right? It's going to be the highest. For human beings, does anybody remember what the degrees of body temperature are in Celsius for human beings? 37 degrees Celsius, right? 98.6 Fahrenheit, but that translates to about 37 degrees Celsius. So, based off of that, where do we expect to see the optimal temperature for lactase if the lactase came from humans? At about 40 degrees, right? For the time points we're taking, at about 40 degrees. So we expect to see the highest levels of glucose here. What do I expect to see as I start going farther and farther away from that optimal temperature? I'm going to see a decrease in glucose. So maybe I have a little bit still produced at 25 and 60. But then I'm probably going to start to see lower levels when I get to 80, 100, and then also 0. We'll come back and we'll discuss what's happening there. But let's get to our bacteria. So, these were potentially thermophilic bacteria, and you were told, I believe, in the lab manual that that implied a potential temperature to be their optimum. And that temperature was about 55 degrees Celsius. So based off of that, if it's bacterial lactase, where do I expect to see the highest level of glucose on this temperature range? At about 60 degrees, right? So maybe I'll see high levels of glucose here. And then I expect to probably start seeing lower levels as I get farther and farther away. Okay, so let's see a decrease there, and then there. Okay? So, just so everybody understands, if I see the highest level of glucose at 40 degrees, that implies it's human lactase. If, however, I see the highest level of glucose produced at 60 degrees, that implies it's bacterial lactase. Now, I want to talk about what's happening at the ends of this temperature range. That is, what's happening here at 0 degrees versus what's happening here at 80 and 100. So, why do you think I see such a low level of glucose production at 0 degrees? What's happening with the molecules there? They're just moving too slow because the kinetic energy is so low. So here, molecules move slow. What's happening over here, though, at 80 and 100 degrees? Denaturation. Good. So, understand the fundamental difference between this. If I pull my enzyme out of 0 degrees and put it at 40 or 60, that enzyme is still functional. But that's not the case if I pull the enzyme out of 80 or 100 degrees. Denaturation is the unfolding of the enzyme, and that results in a loss of activity. Questions, concerns? All right, let's go to the next exercise that was also kind of in this same vein, only instead of determining optimal temperature, we were determining optimal pH. So again, we had a slew of pHs that we utilized. And again, we're trying to determine if it's bacteria or human. All right, now, does anybody remember where lactase is found in humans? Small intestine. Stephanie, do you remember what the pH is in the small intestine?
7.
About 7. About 7.3, 7.4. It's pretty darn close to neutral. If it leans on one side of the pH scale, it's typically a little more basic. Okay? It's the stomach that's acidic, but the intestine is pretty close to neutral. So knowing that, where do we expect to see our optimal pH for human lactase? At about 7, right? So we would expect to see our higher levels of glucose at 7 if this enzyme came from humans, and then we're going to start to see that amount of glucose decrease the farther out we get. Okay, now the bacteria in question were not only thermophilic bacteria, but it appeared that they may have also been bacteria that predominantly live in an acidic environment. So given that information, where would we expect to see the optimal pH for these acidic bacteria's lactase? 2 or 4, right? So somewhere around here, either at 4, I believe technically it was supposed to be about 4.5 if it was from bacteria. And then again, we expect to see a drop off the farther away from this pH we get. Okay? So, in theory, for bacterial, typically, on average, I think you should have hopefully seen around 4 if it was from bacterial lactase. Or, I'm sorry, if the lactase was from bacteria. And you should have seen an optimal pH of about 7 if the lactase in question came from humans. Now, unlike temperature, with pH, there is no slow molecular movement. If you see a loss of activity at either end of the pH scale, it's always because of denaturation. Okay? So, are there any questions about the optimal temperature or optimal pH experiments that were performed? All right, so let's get to the 2 final experiments, which many students tend to find to be the most difficult experiments to comprehend. So let's go ahead and talk about those final 2 experiments. So these final 2 experiments, we're not trying to show that it's from humans or bacteria. What we're ultimately trying to do is we're trying to determine some of the more refined properties of the lactase enzyme. Okay, so 8.3 isn't too terrible. This is just determining the specificity of lactase. Now what this ultimately is this is asking a very fundamental question. If you put lactase in a solution with something that looks very, very similar to its substrate, will the enzyme still bind to that something with the same amount of binding capacity that it does to its substrate? Okay? And so the molecules that we were looking at in this experiment were lactose and maltose. Lactose and maltose, by the way, have different structures but the same molecular formula. What do we call molecules that have different structures but the same molecular formula? Isomers. These two molecules are isomers. So what we're asking is, can lactase actually tell the difference between these two isomers? Remember, this enzyme can't think. This is all based on how well it binds to one over the other. And so what we then did is we took lactase and we added it to each of these tubes. And then we incubated them and we simply measured the glucose between these two tubes. And the question we're asking is, did we see a difference in the amount of glucose produced? Because if we did, then lactase is specific for one of those two molecules. And does anybody remember which tube had more glucose in it? The lactose. So the lactose tube had a greater amount, or as you crazy kids do nowadays, this, okay? I've seen it on Twitter, I know how it works, all right? Now, the glucose was greater here than it was here, and what we can deduce from that is that lactase is specific for lactose. Because if it wasn't, we would expect to see either the same amounts of glucose in each tube, or we would expect the maltose tube to have more. What enzyme do you think is specific for maltose, by the way? Maltase. Good. All right, any questions about the specificity experiment? I think it's pretty straightforward. Let's talk about the final experiment. This is the one that always throws students for a loop. Cofactors of lactase. All right, so let's come back real quick before we get into the specifics of this experiment. I want to give you one final example of why cofactors are beneficial for enzymes. So again, here's my generic enzyme. But let's say that this time, the substrate for this enzyme looks like this. Can that substrate be bound by that active site as it currently exists? No. So, what would a cofactor do? Well, a cofactor can sometimes be used to fill in part of the active site. So the red here would be my cofactor, filling in that portion of the active site. Now, does this active site look, with that cofactor, like it's now ready to bind to this substrate? It does. So, follow-up questions just to make sure we're all on the same page. If I don't have cofactor, can I bind the substrate? No. If I do have cofactor, can I bind the substrate? Yes. Okay. So in terms of lactase, remember what we're really looking at is glucose production. So if lactase uses cofactors and I don't have those cofactors available, do I expect to see higher levels of glucose or lower levels of glucose? Lower levels of glucose, because lack of cofactors means no lactase activity. No lactase activity means reduced levels of glucose. Okay, so that's the first part. I'm glad we're all on the same page. Now let's get to the part that really confuses students. The cofactors we're actually trying to analyze here are calcium and magnesium ions. Those are our potential cofactors. To test whether or not lactase needs them, we need to take them out of solution. Okay? So, in these tubes, there are several things that you add. First and foremost, you had two tubes in this exercise. One was called the control tube, and the other was called the EDTA tube. Now before we get to adding the lactase, let's talk about what we had in each of these tubes. In the control tube, we had water. In the EDTA tube, we had a substance called EDTA. Then, to each tube, we added milk. Quick question. Technically, the cofactors are in both of these tubes right now. What solution has the cofactors in it? Milk. If you think about it, you probably have always heard milk is an excellent source of calcium. Calcium is one of our potential cofactors. So the cofactors are in the milk. Now, before I add the lactase, I put the milk in each of these two solutions. Now let me make something abundantly clear because this is something that students always get confused. EDTA is not the cofactor. The calcium and magnesium in the milk are the cofactors. EDTA is what's known as a chelating agent. Now let's say that all of you in the audience are the enzyme, and your function as an enzyme is to come up on the board and write your name. These markers are your cofactors. They're going to make it so that you can write your name on the board. Okay? So, in this tube, the markers are just sitting up here in that little rim along the board. So, would you be able to come up to the front and write your name if you needed to? Absolutely. In the second tube, though, I'm EDTA. So before you can come up here, I'm going to snatch up all of these cofactors. Can you now write your name? No. So, which of these two tubes represents a reaction without cofactors? EDTA, okay? So, the final component you're going to add here is you're going to add lactase to each of these tubes. You add lactase to each tube. And then again, just like we did over here, we want to measure the relative amount of glucose that is produced by each of those reactions. Which tube do you expect to have more glucose? The control. The control should have more glucose because in the EDTA tube, those cofactors have been bound by EDTA, and the lactase cannot use them to break down lactose. Does that make sense? Questions, concerns, anything I can clarify for people? Yes?
What did you say EDTA is again?
EDTA is called a chelating agent. A chelating agent typically is just going to be a molecule that readily binds to metal ions. Okay? So if you added in any other metal ions, EDTA would probably bind to them too. Iron, copper, anything like that. All right, any other questions?
You said it binds to metal ions?
Metal ions. Calcium and magnesium are actually metal ions. Okay. All right, so we're done with enzymes. Everybody ready to move into respiration? All right.